Good morning, everybody. This is Statistical Computing and Machine Learning. This is Nicolas Zabara speaking. So today we will review prior models. This is obviously a subject we have covered extensively in earlier lectures, but I want to bring some new components and maybe some new ideas as to how we select prior models. All right, so let's see what the topics today will be. We are going to go back and cover again once more conjugate priors, and I will introduce this new concept of what we call exponential family of distributions. So we will see actually that many of the distributions we have used up to now in the course all fit under this general umbrella of what we call the exponential family of distributions. So we will talk a little bit about that. We will introduce the concept of using mixture of conjugate priors, and we will see the mixture of conjugate priors actually leads to a mixture of conjugate posteriors, and so that will be a useful concept. And we will try to discuss about non-informative priors. So priors basically that introduce as little subjectivity as possible, and we will do this either directly by introducing these non-informative priors or indirectly by taking informative priors and pushing them to their uninformative limit. And we will try to see how the two approaches compare to each other. We will talk about translation and scale invariance and the type of non-informative priors that they lead to. We will introduce today Jeffreys non-informative prior, and we will see how those non-informative priors coming from Jeffreys' principle basically deviate from other approaches. We will compare these things to robust priors, and I believe we already have discussed about robust priors being basically distributions with heavy tails. So we will see how these other prior models compare versus robust priors. And so that will be the end of the lecture today. So the goals will include to understand what is the exponential family of conjugate priors and being able to generalize our models using these exponential family distributions. We will learn about the translation and scale invariance, introduce and understand how these Jeffreys non-informative priors are being defined and how they compare with robust priors. And finally, we have to say a few words about how to use a mixture of conjugate priors and how to actually do modeling, how you compute the posterior when you use a mixture of conjugate priors. By the way, let me just say, we will see this, we are not going to prove it, that somehow if you use a mixture of conjugate priors, in principle, you can approximate any sort of other prior model that you may have in mind. All right, so using this mixture of conjugate priors can give you, any other prior model. Of course, computationally, that may not be an efficient approach to follow. Okay, so let me introduce the general setting for the selection of the prior model. All right, we have seen up to now using Bayes' rule that, once you have your likelihood model and you do choose some prior, effectively the Bayesian inference process is rather mechanical. You can define from Bayes' rule the posterior of your parameters. Using that, you can define your predictive distribution, and we already have talked about how to do model selection. So in many ways, once the prior is set, things are rather mechanical. But one of the things we need to emphasize that the prior comes with subjectivity. So if you ask two individuals to come up with a prior model for the same physical setting, most probably they will give you a different choice for a prior model based on their prior knowledge of that problem and their prior experience in working with Bayesian inference. All right, so, but what does subjectivity mean, right? Subjectivity may be something that people want to criticize and say, well, if your prior is subjective, maybe your results are subjective, they don't mean anything, okay? However, I want to make clear this lecture that subjectivity does not imply in any way that the approach to selecting a prior is unscientific. So if you do have any prior knowledge on the particulars of the problem, then your prior should try to represent that prior information, okay? And we have seen various examples in the class where that has been the case. For example, when we talked about interpolation of data, you remember that example with conditional Gaussian distributions, we introduced a smoothing prior, right? We said we anticipate to fit functions that vary smoothly. And so that is a scientific knowledge that somehow comes to be represented with a proper prior model. A smoothness prior in that particular case. So subjectivity in no way implies that our approach to selecting a prior is going to be unscientific. All right, and as I mentioned, a key ingredient will be to discuss about, of the lecture today, to discuss about these uninformative priors, because in many situations, if you are frustrated from the lack of any useful prior information, you may want to use an uninformative prior. And we already have seen with the Edwan smoothing discussed in an earlier lecture that even in the case of completely uninformative priors, you actually do get some effect in your predictive distribution, and that Edwan smoothing that we discussed was a typical example. So in many ways, someone can argue after the lecture today that even uninformative priors, after all, they are not really uninformative if they do affect the predictions that you make. Okay, so we will talk a little bit more about this as we move forward. Okay, so we will start actually discussing with informative priors, all right, and the type of information that these priors can bring will be based on our personal subjective beliefs, but also, maybe you have some historical data, you have some insights on this problem, maybe you have solved similar problems, and also at the end of the day, it may be also an issue of mathematical convenience, as we will see with these conjugate priors. They make the calculations easier, so that may be in your considerations as well. So the typical subgroups of informative priors will be the conjugate priors, this exponential family of distributions that we will discuss today, and of course what is called maximum entropy priors. I am not going to elaborate in this course about these maximum entropy priors, but effectively, if you're trying to put a prior model and you have some constraints in the parameters, effectively these maximum entropy priors are the priors that make no further assumptions beyond the satisfying the given constraints. So if you like, they're as uninformative beyond those constraints as possible. Okay, they're maximum entropy priors. And so lots of the things we will say are directly applicable to maximum entropy priors, but you can find more information in the literature if this is a topic of interest. Okay, so let me remind you what is the idea of a conjugate prior. So let's suppose that we have some likelihood that I denote here as f of x given theta, and that likelihood comes from some family of distributions that I call it capital F. Okay? Now, we're going to select a prior coming from some family of distributions that I call P, and we're going to say that P is conjugate to F when the posterior turns out to be in the same class as this family P from where my prior comes from. Okay? So the idea here is that somehow once you introduce this prior, the posterior is going to turn out to be in the same family of distributions as the prior, but only with updated parameters. So that makes things really very convenient, because effectively, if let's say your prior is a beta distribution with parameters say 0, b0, after seeing capital N data, you will simply update your posterior to parameters AN and BN, and your objective will be simply to calculate what those new parameters are going to be. So that's the definition of a family of prior distributions being conjugate to the family of the likelihood distributions that you use. And obviously this is computationally and analytically extremely tractable situation to have. And the example that we have seen hundreds of times in this course is this coin toss experiment. So if theta is the probability of heads and tails, and you use a likelihood that is binomial, so you do n experiments and you collect, let's say, NH heads, then it comes out that the posterior is a beta distribution with parameters A plus NH and B plus N minus NH. Okay? So you can see the only thing you have done here, simply you updated the parameters A and B with the counts of heads and tails. Again, we have done this calculation before. There is nothing here beyond applying Bayes' rule and multiplying the prior with the binomial likelihood. So the nice thing with this type of conjugate priors is the fact that they provide sort of a certain physical intuition to these updates from the prior to the posterior, and you can actually see here, since NH is the number of heads, in many ways you can interpret A as being the pseudo count of heads before you actually do any observations. So effectively, it's like your prior brings you some number of head observations before you see any data. And similarly, B is like a pseudo count of tails before you see any data. Now, do you really need to take advantage of this appealing interpretation? The answer is no, but I just bring it up because you can only have this interpretation in this setting of conjugate priors. All right, so usually you will use a conjugate prior because the calculations are very straightforward. In many ways, these conjugate priors, even though they are informative, they bring you minimal information to the problem, but there is no certainty that they bring robustness. So you will need to actually, for example, in this particular case, maybe conduct some robustness analysis and see how does your posterior varies when the parameters A and B of the prior vary. Right? This is very important because if you have very limited data and you see significant changes of the posterior when you change the parameters of the prior, then you may need to select another prior that is more robust. Okay, so let's go and introduce this exponential family of distributions. So the exponential family of distributions is a whole class of distributions that fit under some generic form that I am going to give to you right now. So here is the generic form. So we have a family of distributions with parameters theta. D of x here are your sufficient statistics. So it's all the information that you need from your data bold x to compute the parameters theta. This dot here in general is a vector inner product because t of x will be a vector. And so we have some function of theta, some function of x, and then we have the sufficient statistics dotted here with some function of theta. All right. There is an alternative form that you can write this exponential family of distribution, and this alternative form, the only thing that it differences is pulling this c of theta inside the exponential with this function psi of theta, and everything else looks practically the same. So you may see in the slides either I'm using the form on the first equation or the form on the second equation. They're practically the same. Once you know c of theta, you can compute directly what psi of theta is. Now, there is a simple case. If it happens that your distribution fits in this form where the sufficient statistics are basically x, your data. And so here you simply have a dot product of theta dot x. So in this case, the parameter theta is in Rk, and also your data are in Rk. So this family of distributions is called the natural family of dimension k. So we will see in some of the examples, for example, when I refer to the univariate Gaussian with a known mean, we will see that it fits on this natural family of distributions with dimension k. All right, so we will see more when we discuss examples. But again, these first two formulas are the definition of what we call the exponential family of distributions. In a little while, I'm going to give you a whole table that you will see that almost, not almost, but the majority of the distributions we have seen do fit within this exponential family of distributions. All right, so let's take a simple example where we have a likelihood that is Gaussian, and I take here the variance to be 1. So my main unknown is the mean theta. And so does this fit, this likelihood fits under this exponential family? The answer is yes. So if you expand this, okay, and you remember we're looking inside the exponential the terms that involve theta, so the x squared will move outside, okay, and here I'm going to have x times theta, the 2 will cancel out, okay, the minus will cancel out, so you can see actually that this belongs to the natural family of distributions, exactly as we discussed before, and also we see that the sufficient statistics t of x is in this particular case equal to x. If you take both the mean and the variance for the univariate Gaussian to be unknown, so your vector theta will include both mu and sigma squared. So in this case, you can actually see that the distribution fits the exponential family, and I'm giving you here, if you do the algebra, I am giving you a complete description of what this function c of theta is, h of x is, r of theta is, and also psi of theta is. Okay, so and as we have discussed before, the definition of the sufficient statistics here, and in this case I'm taking x and minus x squared over 2, certainly is not unique, but as we know, some combinations of x and x squared need to be there in my sufficient statistics. So in this particular case, I take t of x to be x and minus x squared over 2 simply because I want to get as easily as possible this particular form. So you notice that here r of theta, it turns out to be mu over sigma squared and 1 over sigma squared. Okay? Again, where are all these equations come? Take this exponential, right? Expand the square, and then try, to put it in this form where t of x is given by this particular vector. Okay, so again, I emphasize that in this case, this dot here is an inner product for my two vectors, r of theta and t of x. Okay, we can, of course, in this case, extend this to, more complicated problems, right? But let me just try to be a little bit general here. So let's say my likelihood, it's in the exponential family and looks like this, okay? And you can see now that you can select a prior that somehow has a similar form with the likelihood in a way that when I multiply those two to compute the posterior, I get a posterior that is in the same family of distributions as my likelihood, and this is what I have here. If you multiply those, you can see that your sufficient statistics now, or actually this prior parameter mu is updated to be mu plus t of x, and this lambda is updated to be lambda plus 1, okay? Simply by multiplying my likelihood and the prior. So this is a nice example of using a conjugate prior, but not just using a conjugate prior, but actually all of the distributions that you see here, they all come from the exponential family of distributions. Okay, so in this particular case, you can see that the posterior is actually the same is like the prior, the same family, but with updated parameters that here they are mu plus dx, and instead of lambda have lambda plus 1. So that's the interpretation that I gave before, that simply you have to update the parameters. You have to update your prior parameters using your data, or in some alternative way, you have to update the information that your data bring with the pseudo counts that the prior brings to the problem. Okay, let's take an example again with a Gaussian, where both the mean and the mean is unknown here, but the variance is known. All right, so sigma is known, but the mean is unknown, and we already have seen hundreds of times, right, that the conjugate prior for the mean for the Gaussian is the Gaussian distribution, right? Obviously, I don't have to tell you the Gaussian is in the exponential family of distributions, so not surprised that the posterior in this case also turns out to be a Gaussian, right, in the exponential family. So, and here is the mean, okay, and here is the precision or the inverse variance of the posterior distribution, okay. And actually, not surprisingly, the predicted distribution in this case comes also to be in the same family. It is a Gaussian, right? So if you take the likelihood times the posterior and you integrate the parameters out, you can do this easily. It's given in another lecture. Effectively, you have to close the square on theta, so you can get the normalization factor of a Gaussian, and then what is left is a distribution on X that gives you this nice Gaussian, okay? So that's a typical example of using conjugate priors that belong to the exponential family of distributions. Now, you can repeat the same example with this Gaussian with a known mean when you have lots of data, all right? So you can show, and we already have shown this, that the posterior turns out to be a Gaussian that has a mean mu n and variance sigma n squared, so the subscript n, it reminds you that these are posterior parameters after you collect n data points. But I wanted to bring to your attention how, for example, the variance of the posterior looks like. If you look carefully after some rearrangement of the formula, you notice that the variance of the posterior, it is sigma squared divided by n plus n0, where I have defined n0 to be sigma squared over sigma 0 squared, is the ratio of the variance of my likelihood divided by the prior variance. So when you look at this formula, you have n here is the number of your data points, and n0 is effectively, you can interpret it as the pseudo number of data points that the prior brings to your problem, right? So before you actually do any collection of the data, the prior brings you information that is equivalent to n0 observations. And again, this interpretation is completely unique to the exponential family of distributions. And again, it's only useful when you do get the final analytical results. If somehow they don't have that interpretation, and means most probably your algebra is wrong, okay? But beyond that, you don't really need to worry about using and taking advantage of this interpretation. Okay, and again, these are mu n and sigma n squared, and I will not elaborate more because we have seen these results in earlier lectures. All right, so here is a table that provides various likelihoods, all of them coming from the exponential family of distributions and multiplied with their conjugate priors, and you can see the posteriors obviously they are in the same family. And we have seen a lot of these things before, right? So I can bring to your attention, for example, this is the case of the Gaussian with a known mean, right? That's what we just discussed in the previous few slides. We have seen the case of the binomial distribution and using a beta prior for theta, right? Theta is the probability of heads, and we show that this is the posterior. Generalization, of course, of this is the multinomial with a Dirichlet prior, and the posterior is also a Dirichlet. And you can see the prior counts are added to the data count, so A1 plus X1, AK plus XK. And then, of course, we discuss also the case of the normal distribution with unknown precision theta, and the conjugate prior is a gamma, and the posterior turns out to be a gamma. And so these are convenient formulas that remind you that all of these distributions that we have seen fit in under this exponential family. If you go to Wikipedia, you may see additional results on the exponential family, but this is a useful table, and I think this is all that we need in the context of the lecture today. Okay, let's talk a little bit about mixture of conjugate priors. Okay, so the idea here is conjugate priors are appealing, and because I already mentioned that somehow with a mixture of conjugate priors, maybe you can approximate any sort of a prior model, so then why not use some mixture of conjugate priors? Maybe the algebra will be easy. And it turns out that the posterior, it's also a mixture of distributions from the same family as the prior. So let's see how this thing is going to work with some algebra. Okay, so let's say that you're going to do your coin experiment, and you want to account for the fact that your coin may be a fair coin. So that's a nice prior for a fair coin, but maybe your coin is unfair. So to allow for both possibilities in your prior model, what you will do is you will use a mixture of the fair and unfair beta priors. Okay? So the question is, how do you do actually calculations when you have a mixture of these conjugate priors? How do you do the algebra? And of course, again, we're going to be working under conjugate priors from the exponential family. So let's see some of the algebra. So let me assume that my prior model is this weighted average of these prior models pi I of theta. So I have I have capital K priors, pi 1, pi 2, pi capital K, and I weight all of them with Wi. Obviously Wi, the summation of the Wi's is equal to 1. And I am writing this in also a more interesting way that you see here on the right side of this equation by introducing a hidden variable z that tells me what prior I am using. Okay, so you can see here, right? I mean, these two equations are the same. Okay. Now, if you are going to try, let's say, to sample, theta from this mixture of prior models, effectively, you have to sample from a distribution that corresponds to these different weights, and we will see this when we do Monte Carlo. So, for example, you're going to sample pi 1 with weight W1, all right? You're going to sample pi 2 with weight W2. So, in some sense, you're sampling this with probabilities, you're sampling from prior I with this probability P of z equal to I that is equal to Wi. So, this prior weights, you can think of them as corresponding to these prior probabilities of these hidden variables that tells me which prior model I select. Okay, the way that I have written this equation here for the mixture of priors is going to be a fundamental way when we discuss about mixture models later in the course. Okay, but treat of this P of z equal to I as the prior probabilities of these hidden variables. All right, so Wi are these prior probabilities of selecting model I. Okay. All right, so let me try to do now some posterior calculations. So we want to compute the posterior of theta given some data d. So what you will do is you will take your prior, which is this mixture here, you multiply by the likelihood and then normalize the numerator. And I just put everything, this whole normalization factor for convenience, I call it A. So I can rewrite this posterior as Wi divided by A times pi I of theta times my likelihood. Okay. And now I am going to introduce some new weights that I'm going to call them Wi prime. And the way that I'm going to do this is take this pi I of theta times the likelihood, all right? Take this pi I of theta times the likelihood and somehow divide this by the normalization factor, all right, of pi I times the likelihood and multiply by the normalization factor. All right, so when you do this, you're going to have Wi times this normalization factor divided by A, and this is what I'm going to call here Wi prime. Okay. So, and by the way, I apologize here. I realize, just to keep my notation correct, the likelihood here, it would make sense instead of X to use my calligraphic D's for consistency. So they're one and the same thing. And in the post-it PDF, I will correct this mistake. So this is what we derive for the posterior, right? And with this new definition of Wi prime, I have now my posterior as the new weights Wi prime times pi I times f divided by the normalization factor. So if you pay close attention here, this is my prior model I times the likelihood divided by the normalization factor. So literally this term here is nothing else but my posterior for theta under the prior pi I. All right? So effectively the posterior is now a weighted average with my weights being Wi primes of my posteriors, with each of these posteriors computed using separately each of my prior models pi I. Okay, now maybe you can extrapolate that literally because this pi I thing here is nothing else but the posterior when I use a prior model I, all right, you can extrapolate that Wi prime is nothing else but the posterior distribution of the hidden variable z taking the value I, all right. I am going to formally prove this, but really this has no other choice but to be equal to Wi prime. So this is really tells you what weights to use to weight your posteriors after you have seen your data. So this has to be the posterior probability of your hidden variables, right? And I remind you P of z equal to I was these prior probabilities of these latent variables z. Let me just prove that actually this is equal to that, just for completeness. If you use Bayes' rule, and you compute, so you want to compute the posterior of z being equal to I given your data, you write this as your prior, which is Wi. This is the marginal likelihood, okay, when z equal to I, and on the bottom you have the normalization factor, okay. Now, the marginal likelihood, all right, when you use model I is nothing else but this integral of pi I of theta times your likelihood times d theta, okay? And again, I will change this x to a calligraphic d just for consistency. And you can actually see from this and this is my definition of Wi prime. So you can immediately see that Wi primes are literally the posterior probabilities of these hidden latent variables z, and my posterior is nothing else but a weighted average of the posteriors where I use each of the priors, where this weighted average is defined with these posterior probabilities of z given d. All right, so I mentioned there is, a proof, if you want, that you can approximate with this mixture of conjugate priors any distribution, any prior model. But with that said, people don't like actually using this mixture of conjugate priors because it becomes rather complicated to implement in practice, especially when you have many components in the mixture, and part of the computation has to do with the fact that you have to do all of these calculations and compute these mixture weights that may be impractical to do when the number of your models is high. So let me give you an example of this, and you can refer this back to the case of using two beta distributions for the probability of heads. So one corresponds, let's say, to a fair coin, another one corresponds to an unfair coin. And so these are my prior probabilities of z equal to 1, all right? And this is the prior probability of z equal to 2. And we have to compute these posterior probabilities of z. We know what the posteriors using its prior are going to be. We just have to update the prior counts with the measurements, the number of heads and the number of tails that we got. So really the computation is the calculation of these posterior distributions of z. So I have done this calculation, and I'm going to give you the algebra in 1 second. So this is your prior model, and you see it's bimodal because it has a mixture of two beta distributions, and this is the posterior that you get for a particular data set that is used in this example. And I believe the data set, okay, it's here, it's 20 heads and 10 tails in 30 tosses of the coin. So and again, the key calculation you have to do, and I strongly advise you to actually do this calculation, is to calculate this posterior distribution for the latent variable z. So in these calculations, the main ingredient is to compute the marginal likelihood under each prior model. And I remind you from the previous lectures, this marginal likelihood is very easy to compute with the normalizing factors idea that we discussed in earlier lectures. So you can see here, when I use the first prior model, this marginal likelihood is nothing else but the ratio of the normalizing factor of the posterior divided by the normalizing factor of the prior, and this is the normalizing factor that comes from my likelihood. Okay, so effectively we already know what this is. We know what the prior probabilities are. They're 0.5 and 0.5. You can calculate all this summation once you have this marginal likelihood ready to go. And if the algebra that I did here is correct, there is the posterior. It's a mixture of two, beta distributions, and each of those beta distributions corresponds to the posterior you get under each of the priors. Okay? So a very straightforward type of calculation using this mixture of conjugate priors. Now let me give you another example of this mixture of conjugate priors, and this has to do with this biosequence analysis example that we discussed in an earlier lecture when we introduced the multi-nully distribution. If you remember, and you can go back and review this, we were looking at different sequences of the DNA, and we had all of these data sets where every row corresponds to a sequence of the DNA at different locations, and then every column corresponds to a different location in the DNA. And then what we did is in each location that is here denoted by the letter T, we were counting the numbers that we had, the letter A or the letter C or the letter G or the letter T, okay? And we used the multi-nully distribution to come up with an MLE estimate of this theta vector that tells me the probability of having an A, the probability of having a C, a G, or a T in each location T. So what I want to do here, just to bring a useful example of this idea of using mixture of conjugate priors, I want to introduce some latent variable ZT that somehow measures across different locations in the DNA. It looks at which locations are being conserved. Okay, and you remember this is extremely important in the context of this motif analysis. So if ZT equal to 1, a location is conserved, which means in that location I'm going to have only one letter. So in this case, everything is G, okay? If the location is not conserved, ZT equal to 0. So if the location is not conserved, in some sense, you have high probability of observing some A's and some C's and some G's and some T's. And of course, you can take a fully uninformative multi-nully prior to model that, okay? And we will see how to do this in this context of this mixture of conjugate priors. Now, why do I want to bring this latent variable Z that accounts what locations are being conserved? Because the idea here is that there is a correlation of these Z variables from location to location. So if I somehow build a Markov chain that tells me how ZT changes to ZT plus 1, somehow I will be able to extract information from one location and use it in another location. Okay? So what I would like to do is, I would like to build a model of these counts of the letters A, C, G, T in each location, given what ZT is. So if I knew if the location is conserved or not, I would like to postulate a probability model for the counts of A, C, G, and T. And you notice in this probability model, there are no parameters theta. So somehow what I'm going to need to do is I am going to need to start with these likelihood models of N and theta given Z and try to integrate theta out. And integrate theta out here in principle means average for all possible values of theta. And I would like to do that averaging using some prior distributions for theta, but the way this thing is written here, those prior distributions on theta will be conditions on Z. And this is very significant because if I know that the location is conserved, maybe I can use a different prior than if I know that the location is not conserved. Okay, so let's do that. Here is the equation on the top that tells me how to produce this marginal likelihood model given that I know what ZT is. And effectively, this equation, just using the product rule of probability, if you like, and the marginalization rule here, what I have is I have a mixture, if you like, of conjugate priors, all right? You can see it's an infinite mixture. So I am computing this probability of P of n given theta that we know it's a multi-nully, but theta now is coming from all of these prior models, all of them conditioned on Z. So what do you do if the location is not conserved? If the location is not conserved, you can use an uninformed prior, and you can see here this uninformed prior being 1, 1, 1, 1. Now, what about if the location is conserved? So if the location is conserved, you're either going to have all letter A or all letter C, all letter T or, all letter G, the way that we see, for example, this location 7. And we know from the, Dirichlet distribution, if you want to get priors that actually put most of the probability mass in one of these letters, effectively you're going to have to use a mixture of priors that has very high number A1. So here I'm using Dirichlet with parameters 10, 1, 1, 1, and then you're going to use a Dirichlet with parameters 1, 10, 1, 1, and finally 1, 1, 1, 10. And you can see here is a typical example. I'm not plotting precisely this with parameters 1, 1, but you notice here I have a Dirichlet with parameters 2, 2, and 10. They are plotted on a plane, but you can see exactly where the probability mass is. It's in one of the corners. So if I use an equal weight of this type of Dirichlet distributions, it will actually give me either a pure G or a pure T or a pure C or a pure A. All right. So effectively, it will give me a prior that corresponds to the fact that the location, that I know that the location is conserved. Okay. So this is a very nice example that you can bring physical knowledge to the problem, and this physical knowledge comes through these hidden variables Z that account if a location is conserved or not. Of course, I mentioned that you can build a dynamic model that tells you how ZT changes from location to location, and you can do this with a Markov chain, but this is something that we will need to cover later in the course when we talk about state space models. So hopefully we will come back to this example and try to extend it to that situation, and in the context again of this biosequence analysis. Okay, so let me summarize this idea of conjugate priors. We have seen that they're very simple to handle. All right, they have this nice interpretation that can be useful, but they have some deficiencies. Obviously, you cannot use arbitrary likelihood models and make this to work. It is not going to fly. You cannot actually account with constraints using conjugate priors. At least you cannot do it easily. And I mentioned that this approximation using a mixture of conjugate priors can be very tedious because effectively you have to compute the posteriors of this hidden variable Z that we discussed a few slides ago. Okay, so that's all about conjugate priors, and now what we need to discuss is to introduce this idea of non-informative priors or uninformative priors. So the idea here is, if we don't really have any prior knowledge that is useful to the problem, we want sort of not to do anything strange. We don't want basically to do anything beyond what the data decides for us. Okay, so we want to have the data speak on itself, and so we want the minimal subjective information through the prior model that we use, and this is what we mean non-informative prior. Okay. Now, one acceptable notion basically for using this non-informative prior is that they need to satisfy invariance under reparametrization. Okay. And one of the things we're going to see, for example, is, we're going to talk about translation and scale invariance, right? But you can start thinking even before we do any analysis. When, let's say, if you use an uninformed prior that is uniform, and you reparameterize the problem, you change basically your parameters to something else, you know that your new parametrization is going to give you a distribution that is not uniform. So that may have implications, because means you have to be very careful what parameters you use in your problem, because when you say your parameters, follow an uninformed prior, if I go and do even a small nonlinear change in the parameters, that is not going to be the case. So we have to discuss on how this reparametrization and invariance relations affect the type of priors, uninformed priors, that we have to choose in our analysis. Okay, now if it happens that we want to select a prior on a discrete variable that takes capital K values, the most uninformed prior is basically 1 over K. All right, so we will agree that's the case. Now, I cannot do this for a continuous variable, okay? And not only that, right, but if the domain of the parameter is bounded, and I use, let's say, a uniform, prior, effectively, I'm going to get an improper prior. I will not be able to integrate this from minus to infinity and get a value 1, right? So these priors will not be normalizable. This is what we call improper priors. Now, there are some good news. Even if your prior is improper and you cannot normalize it, if somehow you have sufficient number of data, you can show that your posterior is proper, then you're okay. So lots of times we will use improper priors with the understanding that we have sufficient data to make the posterior to be a proper distribution. Okay. Let me mention something else now before we go to details, right? So I'm going to introduce these uninformed priors on their own merit, and then I'm also going to introduce uninformed priors through the uninformed limit of conjugate priors. Okay, so for example, we can take a Gaussian that as a prior for the mean, and to make it uninformed, we can take the variance of that Gaussian to go to infinity. Okay, so the question is, how do these two types of priors, these uninformed priors, are going to to compare with each other? So we're going to discuss at least with some examples which of those provides issues of robustness that we need to worry about. All right, so let's take this example of the coin toss experiment, where theta is the probability of heads. And we already have discussed that an uninformative prior is the uniform distribution, so it's a beta distribution with parameters 1, 1. And I remind you that the add-1 smoothing leads to a posterior mean, that you have to add 1 to the counts of heads and 1 to the counts of tails, and we get this wonderful expression for the posterior mean, right? This is the add-1 smoothing principle. And so here is a question that's something you need to worry, right? So we use a prior that is uninformed, it's a uniform distribution, right? Beta 1, 1 is a uniform distribution, but then you look at the posterior mean and you realize that this prior, after all, is not uninformed, because it has affected the posterior mean in a significant manner by adding this add-1 smoothing to the heads and to the tails. So the question is this really an uninformed prior? Is the uniform distribution an uninformed prior for the probability of heads? Well, if you push this mathematically at least a little bit, you can say maybe the correct uninformed prior is this distribution, okay? This is a beta distribution with parameters 0 and 0. And this is a weird distribution, has 2 point masses at 0 and 1. It's called the Haldane distribution. Certainly it's an improper distribution. You cannot normalize it, but if let's say for the coin example, if you observe at least one head and one tail, the posterior always comes to be proper. Okay, so even using this non-informative prior, the posterior comes to be proper. Now, very few people will actually use this as a non-informative prior for this probability of heads experiment. So what actually people will often use is a beta uninformed prior that has parameters 1/2 and 1/2. And you know, and you may wonder now, wait a second, if the uniform distribution has parameters 1, how is it possible I have a more uninformed prior, beta prior, than the uniform distribution? Well, this beta 1/2, 1/2 prior is going to come up by a completely different framework based on what's called the Jeffreys prior framework. So you're going to have to wait a few slides for me to show you what this new framework is and from where this parameters 1/2 and 1/2 come from. Okay, but remember, beta 1 is the Z1 smoothing that we have used. Beta 0, it's another improper non-informative prior, and this beta 1/2, 1/2, it's what we will call this Jeffreys uninformed prior for the beta distribution. So before we discuss more details of this, let's talk a little bit about this parameterization issue that I mentioned before. So let's take the very simple case that I give you a distribution on lambda, so that's my parameter, and let's say I make this P of lambda to be a uniform distribution. Okay, so that's my uninformed prior. Now, if you go and change the parameterization to lambda equal to eta squared, and you compute the probability of eta, right? So this will be your prior model on eta. Using the change of probabilities, you can see that this is here P of lambda computed at eta squared. So that's the uniform distribution, but then you get eventually this to be proportional to eta because your Jacobian is 2 times eta. So effectively, we started with an uninformed prior on lambda, but we can see once we have a change in parameterization and we go from lambda to eta squared, somehow the distribution is not anymore uninformed at all, okay? So you need to be careful here. If you choose a distribution to be constant, you need to be certain that you're using an appropriate representation for your parameters, okay? Because if the parameters, if you change the parameters, whatever you have assumed in the previous setting is not going to be valid with the new parameterization. Okay, so with that said, let's talk a little bit about this translation and scale invariance relations and what type of prior models they lead to. So let me take, a density model that it looks of the form that you see here, okay? So P of x given mu is f of x minus mu, and you can think of this in your head, you can think of this as your likelihood model. So this, for example, can correspond to a Gaussian, and mu can be the mean of that Gaussian, okay? Now, mu is called a location parameter, all right? And to just get an understanding why I call this a location parameter, if you go and translate x to x plus c, where c is an arbitrary constant, all right? So if I define a new variable x bar, x plus c for any arbitrary c, you can actually, by this linear transformation of variables, you can see that my density maintains in x bar exactly the same form as my original density in x, where now mu bar is mu plus c, okay? So you can appreciate now why I call mu to be, a location parameter, okay? Now, what I would like to do is I would like to choose a prior that satisfies this invariance relation. Okay, I would like to choose a prior that somehow it does not depend on what location I choose to be the origin in my setting. Okay, so let's see how we can do this and introduce this translation invariant prior. All right, so let me formally define what a translation invariant prior will be. Imagine, so we're working with parameter mu, and we're going to look at the probability mass from A to B, okay? And we want that probability mass from A to B to be the same as the probability mass from A minus C to B minus C, okay? So if we shift basically my origin by C, I want the probability mass not to change. So effectively what I want is, I want this integral that you see here, that's my probability mass from A to B, I want it to be the same as the probability mass from A minus C to B minus C. Okay? That's what I will call a translation invariant prior model on mu. If you change the integration from T to mu minus C, all right, so I'm, there is a reason here I put a dummy integration in T so I can go back to mu, so I'm going to substitute T to mu minus C, so that way my limits of integration become A and B, but inside T is going to become mu minus C. So now if you look on the left and the right hand side, the limits of integration are the same, the variable of integration is the same, so what I need to have is, I need to have P of mu to be the same as P of mu minus C, and this has to be true for any shifting of my origin by any number C, okay? Now you can see that the only way for this to be true is for P of mu to be constant, okay? And that's an improper prior, right? That's the uniform prior that we discussed earlier, so that is a translation invariant prior. Now again, because I am using this analog of mu representing, let's say, the mean, let's say, of a Gaussian, if somehow the posterior turns out to be a proper distribution, then you're fine, even though your prior is improper. And so effectively, if your posterior is normalizable, all right, and posterior normalizable means this statement is true. Now this statement obviously is the likelihood times the prior, and the prior is constant, so really this is what I have here, okay? So if it turns out that this is the case, then I'm fine. And to be able to have a likelihood or a posterior that is normalizable, in this particular case for this location variable mu, you will need to have at least one data point. Okay, so you will need to have at least one data point for the posterior to be normalizable. Now, when you use when your parameter is a location parameter, and you don't want to use this uniform uninformed prior, you can actually use, and I mentioned this before, you can use a Gaussian, which is a conjugate prior for the mean, and you can push this the variance to go to infinity. So maybe if you have a computer code that does calculations for the posterior of mu, and your prior is this Gaussian, and you want to see what happens when the setting becomes an uninformed setting for your prior, you can take your prior and give a parameter sigma 0 to go to infinity. Now, will you get the same answers? Most probably not. And the reason you will not get the same answers, because it turns out that obviously you're not going to go and put an infinity here. You're going to put a very big number, but it turns that whatever number you use, it will actually affect the posterior. So your posterior is not going to be robust to the selection of the parameters that you use on the limit of this conjugate prior. Okay, So that's something you need to be concerned about. Okay, let's talk about scale invariant and think of a likelihood that looks like this. Sigma is a scale parameter. And you can, if you change the scaling in C, right, if from X you go to X bar, C times X, where C is any arbitrary constant, your density doesn't change form, and I have defined here sigma bar also to be C times sigma. You can verify that this is the case. And so we will look to find a prior for the scale parameter that is scale invariant, okay? So we would like a density that is independent of the scaling that we use, okay? And so what's the formal definition for a scale invariant? Similarly to the translation case, if I take the probability mass of P of sigma from A to B, we would like this probability mass to be the same as when we integrate from A divided by C to B divided by C, where C is arbitrary. And if you do a change of variables and you put back the limits of integration from A to B with the new variable, the integrating back in sigma, you're going to need to have P of sigma equal to this. And this has to be true, unfortunately, for every C. And if it is true for any C, you can verify that the only P of sigma that can satisfy this is a model that is proportional to 1 over sigma. Okay? So we know now that for scale parameters, the improper prior based on this scale invariant principle, it's 1 over sigma. And by the change of PDFs, when you do transformations, you can verify that in this case, the probability of log of sigma is actually the uniform distribution. So you can think of sigma, in our case, being the standard deviation, let's say, in a Gaussian, right? So I want you to remember that this result, P of sigma, being 1 over sigma, because I am going to come back to this later on, especially when we discuss this Jeffreys analog for this type of improper prior. Now, can you approximate this with an uninformed limit of a conjugate prior? Yes. You can take a gamma distribution with parameters 0, 0, and immediately you will get basically this, improper prior P of sigma equal to 1 over sigma. Okay, and again, just for scale variables, think of the standard deviation in a Gaussian. So here I am actually indicating both this, I'm bringing the mean and the scale sigma. So this is the location variable, this is the scale variable, right? And so in this case, you will use a prior, an uninformed prior that is 1 over sigma. And by the way, if you do the algebra, you will show that if P of sigma is proportional to 1 over sigma, the P of lambda for the precision is proportional to 1 over lambda. All right, you may want to do the algebra to verify that, okay? And again, this limit for P of lambda to being 1 over lambda, you can get it with, as I mentioned before, you can get it with the gamma distribution, and I summarize for you the form of the posterior, so you can see how in this particular case with A0, B0 being 0, how does the posterior will look on this uninformed limit. Okay, so let's try to finish the lecture today and discuss about this Jeffreys uninformed prior. So the Jeffreys methodology, it is very systematic, okay? There is less intuition, it's more information theoretic, but you can, in principle, perform it mechanically once you understand what you need to do, okay? So Jeffreys method uses what's called the Fisher information matrix. And what is the Fisher information matrix? I denote here as I of theta, and I call this a matrix in general, okay? it is minus the expectation with respect to the distribution of your data set of the second derivative with respect to the parameters of your log likelihood. All right? So there is a loss there. So it is minus the expectation with respect to your distribution of your data of the second derivative of the log likelihood. All right? Now, in some sense, when you look at this Fisher information, you realize that it depends in your data. So you may wonder how is it possible that somehow this will lead to a prior model when there is some dependence here through the likelihood. Okay, well, this is Jeffrey's non-informative prior, and we will see that actually provides some very useful results, even if you may get some situations where it seems that the understanding of what prior model means is being pushed to its limit. Okay, so what is the prior model based on this Jeffrey's Fisher information? So Jeffrey said, take the determinant of the Fisher information, square root it, and that's your prior model for theta. Okay, so that's what we will use today. I am not going to elaborate more on this. You can find plenty of information in David Mackay's textbook on information theory, but this is the Jeffrey's prior. Okay, we need to compute the Fisher information, compute the determinant, take the square root, and that is pi of theta based on this Jeffrey's methodology. There is a nice thing with the methodology coming from this Jeffrey's concept, and that nice thing is that this reparametrization is satisfied automatically. So remember, if I go from a parametrization phi to parametrization theta, I have to obey this change of densities that you look at this equation. Well, it turns out that somehow when you compute the Fisher information, because you have second derivatives with respect to phi, if you use the chain rule, the Fisher information for the phi variables and the theta variables, it relates to this Jacobian d theta over d phi square. So when you take the square of this to define priors, you can actually, if I can go back, so when you take the square root of this, you satisfy directly the relation that's given in the first equation that you see on this slide. Okay, so the Jeffrey's prior automatically takes care of this, this reparametrization, so at least you don't have to worry about that context. So let's see what results this actually gives us for simple cases. So I am going to take Gaussian again, where the only unknown is the mean theta. So I'm going to take the variance to be constant. So this is my likelihood. Okay, nothing unusual. I am going to take the second derivative, and this is what you get because theta, the likelihood is quadratic, right? In the log likelihood is quadratic in theta, so I'm going to get a second derivative that is constant, so no need to take any expectations. So pi of theta comes to be the uniform distribution. Okay? Which is exactly the same result that we had before. Now, if you work with a variance, so theta here is not the standard deviation, is sigma square, and you write down the likelihood, and you take the second derivatives with respect to theta. This is what you get, and now you're going to have to take, because you have your data here, xi, you're going to have to take expectations with respect to the distribution of your data. So now what you have is the expectation of this this square here, and if you remember from the way we evaluated the bias nature of the MLE estimate for this the variance, this expectation here, we proved it before, it's nothing else but n times the variance. So this is n times theta. Okay, So theta and theta on the denominator here will cancel. So eventually you get that the Fisher information is n over 2 theta squared. And again, n is the number of your data. Theta is the variance. If you take square roots of this, you come up that the corresponding Jeffreys prior for sigma square, it is 1 over sigma square. Remember before we came up with the scale invariance that the uninformed prior for sigma was 1 over sigma. Now we see that Jeffreys uninformed prior is 1 over sigma square. Okay, 1 over sigma square. And actually, if if you're curious, if you want to compute the probability of the log of sigma square, right, the log of sigma square, then it turns out that to be the uniform distribution. So you can see this Jeffreys uninformed prior that basically it favors small variance. So when the variance is small, the probability it's higher. Okay, so it favors small variance. Let's go to the binomial case and revisit the beta distribution and its uninformed limit 1, 1, right, with parameters 1, 1, and see where that beta distribution that I mentioned many slides ago with parameters 1/2 and 1/2 comes from. Well, it comes from this Jeffreys theory. So if you take the binomial case, right, this is my likelihood. So in n experiments, I get x heads with probability theta. You compute the log likelihood, take the logs here, take the second derivative, compute the Fisher information, take the expectations of x with respect to the probability of your data set. So the mean of x is n times theta, okay? And here is the answer. And effectively now what we need to do is we need to take the square root of this, and what prior comes out of this, the prior that comes out of it is a beta distribution that has parameter 1/2 and 1/2, okay? That's extremely interesting result. So when you see this in papers and in books, you know that this is Jeffreys uninformed prior for the beta distribution. And of course, there are generalization of this to the Dirichlet distribution. Remember the multi-null Dirichlet likelihood and prior correspondingly, they go together. So for that scenario of the multi-nulli with the Dirichlet uninformed prior, the proper Jeffreys uninformed prior has parameters 1/2, 1/2, 1/2. And this is not anything that you will expect, right? The uniform prior for the Dirichlet distribution has parameters all 1. So that's what somebody will assume normally. Or maybe will assume that all the parameters are equal to 1 over capital K, where you have capital K different states. Well, Jeffreys prior, it's none of the above. It's 1/2, 1/2, 1/2, etc. 1/2. So when you see that, remember that that's Jeffreys uninformed prior for the beta distribution. Okay, let me talk a little bit about inconsistencies when they're coming out from this Jeffreys prior methodology. You remember, let's go and try to calculate the uninformed Jeffreys prior for the pair of the mean and the standard deviation, okay, in a Gaussian, in the case of Gaussian data, okay? Now, if somehow we assume in our prior model that mu and sigma are independent of each other, then we can write the pi of mu and sigma to be pi of mu times pi of sigma, and we know the uninformed prior for mu is the uniform, and we know the uninformed prior for sigma is 1 over sigma, so it would be a reasonable thing to assume that the uninformed prior for mu and sigma is 1 over sigma. So what is going to turn out when we use Jeffreys uninformed prior for mu and sigma, it comes out that when we work with mu and sigma jointly, the prior on mu and sigma, it is not 1 over sigma, it's 1 over sigma square. And it may sound, just a little small, tiny change from 1 over sigma, you go to 1 over sigma square, but actually it is an interesting inconsistency from what we learned before with what this Jeffreys analog is going to give us. So if you want to do the calculation to compute this 1 over sigma square, what you need to do is take the log likelihood. This is what I have here. And you're going to have to take derivatives with respect to mu and sigma square. All right. Actually, derivatives with respect to mu and sigma, because that's the variables I work. So you're going to have to take, so this will be the second derivative with respect to mu. This will be the second derivative with respect to sigma. And the diagonal terms will be the second derivative with respect to mu and derivative with respect to sigma. Okay. Will be the joint derivative with respect to mu and sigma. When you take expectations, the expectation of x is mu, so that the off-diagonal terms, they cancel. You take the determinant, and there is pi of theta to be 1 over sigma square, which doesn't agree, with what we have seen before when we take mu and sigma to be independent of each other, okay? So, for example, when you use location and translation invariant priors and you're assuming the two are independent, you get 1 over sigma, but here the result is 1 over sigma square. You can come up with other inconsistencies like this using the Jeffreys prior. All right, so keep those things in mind when you decide to use this. Now, there is no physical information that Jeffreys prior is bringing. As I mentioned, it's a little bit mechanical. It works, right? People are using it often in Bayesian inference. And there is one other very little tiny problem that I will not elaborate a lot. When we did Bayesian inference, in one lecture we mentioned this the likelihood principle, right? You remember, if you have two settings where two models bring you two proportional likelihoods, then the inference for the parameters will give you the same parameters, right? So when you, let's say, compute the MLE estimates from two proportional likelihoods, the answer is going to be the same. Well, it turns out the physical information doesn't actually give you the same prior for two likelihoods that they are proportional to each other, okay? And the standard example that is mentioned in books is when you use the likelihoods corresponding to the binomial and what's called the negative binomial distribution, in case you want to look at this in the literature. All right, so let me just finish with some notes on the robustness, right? So I mentioned before that often you may want to take a conjugate prior and push it to its uninformed limit. So here, for example, if we work with Gaussian data and you want to use an uninformed Gaussian as your conjugate prior for the mean, you may want to use this Gaussian here. So it turns out that when you change the level of the variance that you put in your prior, the results change significantly. And this is a particular case, for example, where you can see that, this is the computed posterior, and you can see the results that you get. This red posterior is with a flat prior, and this dotted blue curve is the posterior you compute with a conjugate prior, okay, using a Gaussian. So the idea here is there is a lack of robustness when you use conjugate priors, and so when you decide to actually use the uninformed limit of conjugate priors, you may want to conduct this robustness analysis to be sure that somehow you don't have significant changes in your posterior induced by small changes in your prior. Now, obviously, if you want robustness in your modeling, you're going to have to use priors that are robust, and we already have discussed priors such as the Cauchy prior or the Laplace prior. These are priors that have heavy tails. And think if you use a prior that has heavy tails, effectively it does not force the parameter to be close to the prior mean. Okay, so the effect, if you like, on the posterior is minimized because these priors put bigger probability on the tails. Okay, so it doesn't shift the whole estimate towards the prior mean the way, for example, a Gaussian prior will do. And here is an example, right? If you, let's say you collect one data point from this Gaussian where the only parameter is the mean theta, and let's say that so you compute, you select one data point x equal to 5, and you want to compute what is theta. So the MLE estimate with one data point will be equal to 5. And actually the posterior mean in this case will also be equal to 5. Okay? Now, let me tell you what is going to happen when you try to use, if you try to do inference using, a Gaussian prior for the mean and pushing this prior to some uninformed limit. Okay, so what I'm going to do is I'm going to take two prior models for the mean. One will be a Gaussian, and the other one is going to be a Cauchy prior. And I'm going to select the parameters of this prior and the Cauchy prior so that somehow the probability mass that each of them assigns to these quantiles that you see here, so if you take the quantiles if you take the probability for theta being less than -1, between -1 and 0, between 0 and 1, and greater than 1, and you enforce both, the parameters, you enforce the parameters in the Cauchy and the Gaussian prior to satisfy this, so that way both priors are in the same footing, so it becomes easier to actually evaluate their performance in Bayesian inference. So if you do that, then it turns out that the Cauchy prior will lead you to a posterior mean that is 4.6, which is very close to the true value. So it's very reasonable, but if you actually use the Gaussian, the posterior mean turns out to be 3.43, which is not a very satisfactory answer. The point here is robustness is extremely important. Selecting the priors and consulting, with some robustness analysis is extremely important. So that way you know what parameters to use in your prior models, or even investigate if what you need to do is you need to use not a conjugate prior, but maybe a prior that introduces robustness to your problem. Okay, so and again, maybe just remember that these robust priors, by having heavy tails, do not force the parameters to shift towards the prior mean. Okay, and if you remember, for example, the posterior mean, it's always some weighted average between the MLE and the prior mean. So a prior with heavy tails does not force you towards the prior mean, and that's what adds robustness in your posterior estimates. All right, so I will finish with the lecture here today, and we will continue in 2 days with a lecture on hierarchical Bayesian models. Bye.